next presentation comes from Alessandro Rigazzi from HPE, who's going to give an update on their SmartSim strategy.
All right, welcome everybody. Good afternoon as of now. So yeah, my name is Alessandro. I'm a research engineer at the HPC and AI EMEA Research Lab in HPE. And today I'll be talking about SmartSim and its last evolution and changes in strategy. So for those of you who weren't here last year or don't know what SmartSim is, I'll just give a brief introduction. It drives along with what's already been said today about the evolution of HPC, simulations, and AI. So over the last, I'd say, 5 to 10 years, we've observed a paradigm shift in HPC. So the old numerical workflows used to be quite simple. You used to have input data, so initial conditions, could be a file, could be hard-coded values. And then you would have this monolithic application, which was like your code you have been developing for 10, 20, 30 years, always updating it with new things you could think of, new algorithms you were finding in the literature. You would just add it to your old C, C++, or Fortran code base. You would just make sure it works for your use case and then move on to the next thing. And then you would execute the code on your input. You would just get the output. The output would be then a file. You would store on the file system. You would analyze it once, maybe twice, visualize it, put it in a paper, present it. That's done. And that was good as long as everything was more or less moving at the same pace, especially numerical algorithms and research were moving at the same pace. But now there is AI in the mix. And AI, as you know, evolves at a very different pace, at a very different rhythm with respect to numerical algorithms and methods. And so now what is more useful to have is a composed workflow where you have, obviously in our case, so we're like what we are developing is something just targeting numerical workflows and HPC simulations. So the core of the engine is always for us the HPC parallel application, so your standard MPI, C, C++, Fortran-based simulation. But then you want to add something new, some new method you found in the literature. It could be ML inference. And now I'm not much of a proposer of replacing the whole simulation with ML inference. I like to think that ML inference can fill the gaps and the blanks you originally filled with approximations or just heuristics or just parameterized models where you just estimate some parameters which your model wasn't capturing, for example, right? And you want to replace that with a machine learning model. Or you want to train the model while your simulation is running. That could be a use case in which you don't want to store all the data you're producing because it's too large and you just want to train the model as you run the simulation. Or it could be something like reinforcement learning where you want the simulation and the training to move together. And then maybe you want to do visualization and analysis. So all of this doesn't work if you use the old numerical workflow, old way of writing code, because you want to be able to separate concerns and have like the HPC parallel application just doing the simulation, the ML inference just doing the ML inference. So just using the best you can find about AI models, for example. So you want to just grab the new version of PyTorch, the new models from Hugging Face, and put it in your workflow, right? So you want to have a separation between the two things. You want to do the same thing for model or for the visualization, right? So what we tried to develop at the beginning, like 5 years ago now, was a way of orchestrating very lightly this whole workflow just by allowing a clear exchange of data. So SmartSim is our solution, and it's an open source library. It's totally open source. It's on GitHub. There's no secret sauce. Everything is there. And it tries to bridge the divide between traditional numerical simulation and data science, right? It does so by putting a database, an in-memory database, starting it and then informing all components of your workflows about its existence, so that then by using our clients, which are super lightweight and very easy to use, every portion of your workflow can communicate with the database. The database is a feature store, so it can also store active code, scripts, AI models that can be executed directly on the database or on the feature store. Currently, it uses Redis as a backbone and Redis AI for executing AI models, but we are moving on from that in the future or in the near future. And what SmartSim enables you to do is using machine learning models in your existing simulations, like in Fortran C or C++, or even in Python, obviously, exchange data across the boundaries of language and simulations, and train machine learning models or analyze data stream from your application in real time. All right. So again, the idea was just to allow embedding machine learning into C, C++, and Fortran simulations, right, and exchange data at scale, right, without touching the file system. And the reason I say this is because as every numerical software developer turned AI scientist, at the beginning I was just saying, okay, let's just run one step of the simulation, dump everything to disk, read it from the AI script I have, dump the inference result to the disk, read it back into the simulation, and that would kill every file system I know of. And that's what many people still try to do as a first attempt. And then they're super surprised when you tell them that if you use an in-memory file system or in-memory database or also a file system, it gets much faster, right? So they test it and they say, oh, well, we have a 20% or 30% speed up by doing basically nothing. And it's obvious because you don't touch the file system anymore and you don't misuse the file system for something it wasn't thought for. And so there are some updates on SmartSim. There's an updated structure, but we start from an old mission. It's always to help scientists and researchers, right? So we just want to empower our users and our community to write modular workflows which can be ported across systems, across workload managers, and across different architectures. But we are now more open. So SmartSim is still maintained and updated by HPE, so we work on bug fixes and stuff like that. But we're more open to external contributors. So in the past, we would talk to users, we would organize hackathons and stuff like that, and then we would just gather all the suggestions, implement them, and then give them to the users and ask them to review them and see if it was the right way of implementing them. Now we are more open to collaborations, and this comes as a result of some very, very good collaborations we've had in the past, where we have seen that the results were incredible and very useful for other users too. And so we develop new features when the users request them. We are not pushing new features unless the community is asking for it. And then SmartSim has moved also in the organization, in HPE. So it was moved from the HPC and AI software group to the labs organization. So now it's incubated by the team I'm part of, so the HPC AI EMEA Research Lab, and it's co-developed with an HP lab in the US, right? So it's like we have another developer on the other side of the Atlantic Ocean. So talking about the new house, this is the HPE HPC AI EMEA Research Lab summary slide. So we are a lab. A lab is an organization which doesn't really push for selling new products as a first thing. It just does research. Our role is that deep technical collaboration with industry, academia, and public sector, long-term technical relationships, and focusing on new technologies, and then driving future HPE products. All things that work very well with SmartSim's philosophy. And then our research interests are also very well aligned: HPC, cloud, AI, and quantum, data movement, analysis and workflows, heterogeneous computing, and novel accelerators, things that we've always tried to support with SmartSim. And we have different engagement models, for example, the centers of excellence and advanced collaboration centers, and then ad hoc projects, and so on and so forth. So I'm part of one of the advanced collaboration centers. I'm part of the LUMI one. We have one with Archer 2, KAUST, GW4, LUMI, Blue Lion, and also one in Australia with POSI working on Cetonics. And for each Advanced Collaboration Center, we have different projects. Sometimes their goals align, sometimes they diverge, and we try to work in strict collaboration with their engineers. And now let's move to a more applied use case of SmartSim. So this is one of the latest, not the last, but one of the latest research paper which use SmartSim. It was published by Bernard Font and others. Most of the simulations were run on at the Barcelona Supercomputing Center. So it, again, as I was saying, the cool thing about SmartSim is that it separates well the simulation and the AI part of your workflow. And this is something very, very good when you want to do, for example, reinforcement learning with HPC simulations, as they did. So the idea is to do active flow control of turbulence separation bubble through deep reinforcement learning. So kind of the big picture. So imagine the plot on the right-hand side to be the profile of a wing, or a simulation of a profile of a wing profile, where you have the bump, which creates a difference in pressure, which then creates detachment and reattachment of the flow, which in turn creates separation bubbles and recirculation. And wherever your flow doesn't flow well and recirculates, you have drag, you have loss in performances, right? And so the idea of the study is to reduce the turbulence separation bubble formation. And they did this applying reinforcement learning, which is something we've seen many times done with SmartSim now. I mean, I think it's the third or fourth group which uses SmartSim exactly for this. So we're very happy that it's kind of spreading in this CFD reinforcement learning community. And so you possibly already know what deep reinforcement learning is. If you don't know, I'll just give a quick recap. You're training an agent, right? So something that has to interact with an environment. If it's deep reinforcement learning, it usually means that you're using a deep neural network as the way the agent decides on what to do, what action to take based on the environment to optimize some reward function that you are defining. And this is cool because in other studies we've seen the same exact environment giving completely different results when they change the reward function. In this case, obviously, they wanted to minimize the recirculation length. So this is just basically a way of characterizing your turbulent bubble. They want to minimize the recirculation area. And yeah, the environment is just composed of 72 probe points. So basically 72 points where you can sample the flow. And then, yeah, they trained on 24 parallel pseudo environments on 8 GPUs. So on each GPU, you have multiple environments. And in more or less a week, they were able to get the training done. How they achieved this? Well, the simulation part. Also, the workflow was launched through SmartSim. SmartSim is So SmartSim has an infrastructure library, which is a Python library, which allows you to interact with the workflow, with the workload manager and the launcher you have on the system. Usually you do it in a Jupyter notebook or in a Python script. So the whole thing was launched through SmartSim, and then SmartSim would launch the simulation on the different nodes, the in-memory database, again, it's a Redis in-memory database in this case, and then the reinforcement learning model running on different nodes. And the simulation and the reinforcement learning model will just put and get data from and to the database, right? So at each step of the simulation, the state would be put on the database and it would be accessed by the reinforcement learning, or trajectories would be accessed, and then the reinforcement learning model would be trained based on the reward function. And so the results are pretty impressive. So this is what happens if you don't try to control the flow. Then in the state of the art, the idea was to put these 6 actuators, which can basically suck or push the air basically around them, right? And the state of the art was to use them periodically. So you would just add some periodic push to the flow, and this would reduce for sure the average recirculation length, but it would also start creating these large oscillations, which then could be actually detrimental for your whole flow and the stability of your, for example, wing. Whereas with deep reinforcement learning, they were able to minimize the surface much better, and especially if you look at the right-hand side here, the far right plot, you see that the average is lower and the peaks are much more contained, and this is very important. So they were able to reach a 25% reduction compared to the 15% which was in the state of the art. Finally, the project I was talking about, where we took the inspiration for the new structure of the SmartSim project, was the OpenFOAM collaboration. So we teamed up with the OpenFOAM data-driven modeling special interest group. OpenFOAM, for those of you who don't know, is one of the most widely adopted open source CFD solvers or library. And we've teamed up to create a submodule, so OpenFOAM operates with modules and submodules that allowed users to seamlessly use SmartSim and our database from the simulation using basically the typical OpenFOAM syntax, right? So we published a paper about this, right? And in the paper, we use SmartSim with OpenFOAM to achieve 3 different types of interactions between AI and numerical simulations. And the submodule was actually accepted by the board, the OpenFOAM board. So it's the official submodule used by the OpenFOAM community to use machine learning in OpenFOAM right now. It has 3 layers, and this was something that came out from the collaboration. So it has, I will just go a bit quicker than usual on this, but like there's the service API, which is the higher level API. It's just, you can just do more or less one thing. You can just send these geometric fields, which is the way OpenFOAM sees data and fields, to the database, and you can get it back from the database. And then you can do not much more, but this is usually enough for the basic workflows you want to achieve when you do, for example, CFD in reinforcement learning. Then there is a bit lower level is the developer API. So they don't interact directly with Redis database. They handle what is called a data set. In SmartSim, a data set is just a construct which keeps all tensors together when you push them to the database, which can be running on any node of your system. And then there is the lowest level, which is the generic API, which is more or less just a one-to-one match with the SmartSim API and SmartRedis API from the OpenFOAM library and language. And so one of the cool things about using this approach where we completely decouple the simulation and every other portion of your workflow is exactly this, that by defining the way you want to communicate, what you want to communicate to the database, then you can put the database on any node of your system. You can maximize resource utilization by using nodes which are best suited for your database, for example. Maybe because you want to run AI in the database and you don't want to run it in the simulation itself, so you will just put the database on the GPUs and run the simulation on the CPUs, right? And that's what's basically enabled by these kind of interfaces we hope to replicate in other libraries too. Okay, I don't think I will go through the recap because this was quite short, but again, everything is available in a public repo, right, for the submodule, so you can download it and use it in OpenFOAM, and the paper which was published and it's open access shows exactly how to use the module and different examples on how this can be used to achieve modern workflows. Finally, we have a very, very good documentation. I am very proud of it. It's hosted on craylabs.org. It gives basically, it has the API and many examples on how to use the container and so on and so forth. So you can just go and browse it yourself. Otherwise, there are many resources. You can always send us an email or go through the repository or, there are some case studies published and so on. And if you go on the repo, don't forget to star it. That's it. Thank you.
Thank you, Alessandro.